tests. Hello and welcome to another discussion series in General Chemistry 2. For this discussion series, we will be talking about acids and bases, and we will learn about the characteristics of acids and bases and the reactions they undergo. So here are some of the topics that we will be discussing in this lecture series. We have the Ardennes acids and bases, the Bronsted Lowry acids and bases, the pH scale, and the buffer solutions. But before we start our discussion, here are some of the common mistakes that we do in our households, which are mixing different cleaning products. However, we should be mindful as mixing some of them might result to poisons which can harm us. Here are some of those dangerous combinations. We have bleach and vinegar. We also have bleach and ammonia. We have bleach and rubbing alcohol, and then hydrogen peroxide and vinegar. Now, let's have a recap first on how we name acids. Remember that we have different types of acids. One of those is the binary acid. So in naming binary acids, the prefix hydro is used to represent hydrogen, followed by the name of the nonmetal with its ending replaced by the suffix IC, and the word acid is added. So for example, we have here HCl. So we have the prefix hydro and then the suffix IC and then the word acid. That's why we have hydrochloric acid. And then we also have HBr, which is hydrobromic acid. So here is how we name binary acids. Now, for naming oxyacids and oxysalts, which is the other type of acid, if you replace hydrogen with a metal, you have formed an oxysalt. A salt is compound consisting of a metal and a nonmetal. If the salt consists of a metal, a nonmetal, and oxygen, it is called an oxysalt. For example, we have NaCl4 or sodium perchlorate, it is an oxysalt. So if it is an oxyacid, we have here perchloric acid, H for HClO4. And then for NaClO4, we have sodium perchlorate. And then for the chloric acid, which is HClO3, for its oxysalt, we have sodium chlorate. And then lastly, we have the chlorous acid. We also have the oxysalt sodium chloride. So how do we define acids and bases? The earliest definition of these substances was suggested by Savante Arrhenius in the late 19th century. So we have here three scientists who defined acids and bases. For Arrhenius, it is a hydronium ion or a hydrogen ion producer, while a base is a hydroxide ion producer. While for Bronsted Lowry, it is a proton donor for the acids, and then for the bases, it is a proton acceptor. Now, for the Lewis definition of acids and bases, we have an electron pair acceptor for acids and an electron pair donor for bases. So we will be working on these definitions as we go along with our discussions. Now, for the Arrhenius acid and base definition, this is the earliest acid-base definition which classifies these substances in terms of their behavior in water. So, an acid, according to Arrhenius, is a substance with hydrogen in its formula that dissociates to yield H3O ion or the hydronium ion. While a base is a substance with OH or hydroxide in its formula that dissociates to yield hydroxide ions. Now, some typical Arrhenius acids are hydrochloric acid, the nitric acid or HNO3, and cyanic acid. And some typical bases, we have sodium hydroxide, potassium hydroxide, and barium hydroxide. Because they are ionic compounds, Arrhenius bases contain discrete hydroxide ions in their structures, but Arrhenius acids never contain discrete hydrogen ions. Instead, they contain covalently bonded hydrogen atoms that ionize when molecules of the acids dissolve in water. We also have to remember that when an acid and a base react, they undergo neutralization reaction. The meaning of this term has changed, as we'll see in the next few slides. But in the Arrhenius definition, neutralization occurs when the hydrogen from the acid and the hydroxide from the base form water, as is in this formula. Now, for the Bronsted Lordy acid and base definition, while the Arrhenius definition correctly predicts the behavior of many acids and bases, this definition is limited and sometimes inaccurate. We now know, for example, that the hydrogen ion does not exist in water. So, hydrogen ion is a naked proton with no electrons, and this concentrated positive charge reacts rapidly with a lone pair in water to form hydronium ion. Although hydrogen ion will sometimes be written in an equation for emphasis, hydronium ion is actually the reacting species. Now, several compounds contain no hydroxide anions, yet they still exhibit the characteristic properties of a base. Examples include the neutral molecule ammonia and the salt sodium carbonate, and as a result, a more general definition of acids and bases proposed by Johannes Bronsted and Thomas Lowry in the early 20th century is widely used today. So in the Bronsted-Lowry definition of acids and bases, they are classified as to whether they can donate or accept a proton, which is a positively charged hydrogen ion. So when we say acids in the Bronsted-Lowry definition, an acid is a proton donor, any species that donate a hydrogen ion. So an acid must contain H in its formula. Now, when it comes to bases, a base is a proton acceptor, which refers to any species that accept a hydrogen ion. So a base must contain a lone pair of electrons to bond to hydrogen. An acid-base reaction is a proton transfer process. So to discuss it in detail, a Bronsted-Lowry acid again must contain a hydrogen atom. So hydrochloric acid is a Bronsted-Lowry base because it donates a proton to water when it dissolves, forming hydronium ion and chlorine. Because a Bronsted-Lowry base contains a hydrogen atom, a general Bronsted-Lowry acid is often written as a general formula HA. So this is the general formula for the Bronsted-Lowry acid. So A can be a single atom such as chlorine or bromine. Thus, hydrochloric acid and hydrobromic acid are Bronsted-Lowry bases. A can also be a polyatomic ion. It can be a sulfuric acid and nitric acid, which are Bronsted-Lowry acids as well. So, carboxylic acids are a group of Bronsted-Lowry acids that contain the atoms COOH arranged so that the carbon atom is doubly bonded to one oxygen atom and singly bonded to another. So, acetic acid, which is CH3COOH, is an example of carboxylic acid. Although carboxylic acids may contain several impurities. Now, for the Bronsted-Lowry base, as we have defined earlier, a Bronsted-Lowry base is a proton acceptor, and as such, it must be able to form a bond to a proton. Because a proton has no electrons, a base must contain a lone pair of electrons that can be donated to form a new bond. Thus, an example here is an ammonia, which is a Bronsted-Lowry base because it contains a nitrogen atom with a lone pair of electrons. So when ammonia is dissolved in water, its nitrogen atom accepts a proton from water, forming an ammonium cation or NH4 and hydroxide ion. So a general Bronsted-Lowry base is often written as B with a colon. So to emphasize that the base must contain a lone pair of electrons to bond to a proton. So a base may be neutral or more commonly have a net negative charge. Ammonia and water are both Bronsted-Lowry bases because each contain an atom with a lone pair of electrons. So hydroxide, which contains an oxygen atom with 3 lone pairs of electrons, is the most common Bronsted-Lowry base, and the source of hydroxide ions can be a variety of metal salts, including sodium hydroxide, potassium hydroxide, magnesium hydroxide, and calcium hydroxide. So from the perspective of the Bronsted-Lowry definition, an acid-base reaction occurs when one species donates a proton and another species simultaneously accepts it. An acid-base reaction is thus a proton transfer process, and an acid-base reaction occurs or can occur between gases in non-aqueous solutions and in heterogeneous mixtures as well as in aqueous solution. So in this image, acid donates a proton to water. When hydrochloric acid dissolves in water, a hydrogen ion is transferred from chlorine to water, forming a hydronium ion, which is the H3O+. Thus, HCl is the acid, and here water is the base, since it accepted the proton. While in the other image, in here, we have here a base which accepts a proton from water. So here, water is the proton donor while ammonia is the proton acceptor. So based on this reaction, water here is an acid, and then ammonia is the base since it is the proton acceptor. So note that water is what we call amphiprotic since it acts as a base in one case and as an acid in another case. So the Bronsted-Lowry definition of acids and bases is a more general definition of acids and bases. An acid is any substance that can donate a proton, while a base is any substance that can accept a proton. So remember that this definition is not restricted to aqueous solution. And that ends out the first part of our discussion series. Thank you for listening.